Hi, this is Mark Weitzman. Welcome back to a series of videos solving a problem in the complex analysis class taught by our Russian friends at MISISx. And so last time we finished by showing where the locations of the potential poles are, where the branch points are. I now want to start by calculating the reference point. I'm going to calculate the phase of 1 minus z cubed to the 1/3 at that reference point, which is at the start of the contour. And we were given this fact. Now, if you substitute very simply f of rho e to the minus 2 pi I over 3 into the function for f, what are we going to get? We're going to get, we have to have 1 divided by h. Remember, h is this, so I'm just going to substitute that. H of rho. I'm trying to make my rho's curly so you don't confuse them with my e's. Minus z. But z is this. So we have this, rho e to the minus 2 pi I over 3. And this, we're told, is equal to minus 1 over 2 minus 1 over 2 rho e to the 2 pi I over 3. Now, the first thing you should do is, they sort of like tried to trick you in this problem, but put this downstairs instead. Then you can see exactly what's going on. E to the minus 2 pi I over 3. So now you can see what we want is, if h of this is equal to that, if this is equal to minus rho e to the minus 2 pi I over 3, we get exactly what we want. Minus 2 rho e to the minus 2 pi over 3 with a minus sign. So this shows that at the reference point, h of z, let's call it zr for z reference point, is equal to minus the absolute value of zr times e to the minus 2 pi I over 3. So our phase is essentially -1. I could combine it, but I'm going to leave it outside. E to the minus 2 pi I over 3. This is the starting phase. For h of z. So we got to remember that. So now, using this starting phase, we can now, using the standard techniques that they taught in the course, we can now calculate the values of the poles of the function h at each of the poles. So let's, I'm going to review some stuff here and let's start doing that. I'm going to like draw this diagram over and over again, but I'm always going to keep that one up there. But I just want to show you what's going on as we do this. Okay. Here are the poles, potential poles. Okay. So the methodology that we developed in the course, I'll write it down here, was we evaluate a function, we analytically continued it. This is defined by 1 minus z cubed to the 1/3. We calculate this by starting with h at the reference point, zr, which we know. And then we multiply by the absolute values of h of z over h of zr times the phase that accumulates, the difference, del arg h of z. So you could see sort of this is essentially, this divided by this is essentially the starting phase. We'll get whatever the absolute value is relative to where we started, and then we're going to enter the accumulated phase of the new function. Now in our case, this is going to be equal to rho. We calculated the starting phase last video. We're going to have the absolute value of h of z, our reference point. It's really at rho equal to infinity, but it will cancel anyway here and here. See, these are going to cancel. And then I'm going to have e to the del arg h of z. But, continuing on, minus 1 e to the minus 2 pi I over 3, absolute value of h of z. Sorry, this should be like. Now, h of z is basically g of z to the 1/3. So whatever phase we accumulate in g, we'll divide it by 3. So we're going to get e to the I, because it's easy to calculate the phase changes in g, del arg g over 3. Remember that g of z equal 1 minus z cubed. And that splits into linear factors. Okay. And I'll write it again as equal to minus z minus e to the minus 2 pi I over 3, z minus 1, and z minus e to the plus. Okay, so what we'll have to do is we'll determine the change in phase for each linear factor. And in a sense, divided by 3, which we're already doing over there. So if you look at it, let's say z is the pole. Let's say we take this pole over here. So when we calculate, what we're doing is we're sort of saying this is the reference point. And we sort of draw an arrow from the pole to the reference point. I'm sorry, that's wrong. We draw an arrow from the branch point to the reference point. And then we draw an arrow. I'm going to shift this a little bit, and then we draw an arrow from here to here. So basically, when we move this point from here to here, our phase arrow sort of follows along this contour. It's there, and then it's there, it's there, it's there, it's there, it's there. So you can see that in this particular case, it rotated by pi in the counterclockwise direction. So del arg for that factor is equal to pi. We also have to do it for this branch point, for each branch point. Each branch point corresponds to these solutions, and the z corresponds to the pole. So it's just like vector subtraction. Now, from this branch point, you can see that what happens is we go from like here, this angle, we follow this contour, and we end up over here. So we go in the clockwise direction. That's why I'm going to write it as minus theta. In this direction, we rotated, so we get a phase change minus theta. And now, from this branch point, I'm going to draw this. Remember, this is really at infinity, so I'm going to draw it like parallel to this line. So we start from like here, and we rotate, and here's the final point. And it turns out these two angles are equal. You could see symmetry-wise, if you look from this line, it will be very obvious that these two angles are equal. So I wrote equals. Let me write this a little better. Del arg for the function g at e to the minus 2 pi I over 3 divided by the cube root of 2. So this is this pole over here. This is equal to pi plus theta minus theta equals pi. Now, it's really simple geometry to show some facts, and I'll just state them right now, that along any of these points on this line, from the origin to the pole, any of these points will have the same phase change of pi. And not only that, that will also apply to any of these things. They'll have the same phase of pi, and they'll have the same phase change of pi. So all of the poles have the same phase change of pi on the first sheet. So consequently, the del arg at the poles is equal to pi. And now, using this formula, we're going to get h of z at the poles is equal to minus 1 times e to the minus 2 pi I over 3 times e to the pi I over 3. This is going to be equal to, minus 1 is e to the pi I. So I have 3 pi I over 3 minus 2 pi I over 3 is pi I over 3 plus pi I over 3. We're going to get e to the 2 pi I over 3. And then we have, I left out the absolute value here. And then it's going to be multiplied by, they all have the same absolute value, 1 over cube root of 2. So this is the value of the function h at the poles on the first sheet. We didn't cross any branch lines when I went from here to here. You know, no branch lines were crossed. We're still on the first sheet. So what I'm going to do now, I'm going to come back in the next video, and I'm going to show, we're going to calculate the function f using these values. And we'll see that, in fact, we only have a pole, a real pole on the first sheet at one of these points. And then we'll come back, and I'll see you in the next video. Thank you.